Okay, polarity is related to acid strength because if a molecule is more polar, it means that the charges have a greater separation. So like the positive end is more positive and the negative end is more negative. So the electronegative side of the polar molecule is like pulling on the electrons more, so much that it's almost going to pull them away, but not quite. And so since it's really polar, like if it's HCl, we know hydrochloric acid is a strong acid. This side is our partial positive, this side is our partial negative. But this side is very negative because chlorine is really electronegative. So because of the fact that this is a really polar molecule, this hydrogen is barely hanging on to that molecule at all. And so it's going to fall off of the molecule fairly easily. And so that means that you have greater dissociation and a stronger acid. So the more polar the molecule is, the stronger the acid is going to be because of the fact that that hydrogen is just barely hanging on, so it dissociates easily. The one exception to that is hydrofluoric acid. We know that this, of course, is very polar because fluorine is super electronegative, but we also know that this is a weak acid. It's very polar, but also the bonds are very strong, probably because the fluorine is just a really small atom, and so just that charge is still kind of close together and holding that bond in strong. So if the bonds are strong, then it's a weak acid because it holds on tightly to the hydrogen and it doesn't allow it to just kind of leave the molecule and dissociate very much. So those are weak acids. Stronger bonds, weak acids. Weaker bonds are stronger acids because you get more hydrogen. All right, so now for the oxyacids, they're really just the ones that have oxygen, which are mainly the ones that have some kind of, well, they are the ones that have a polyatomic ion. Hydrosulfuric acid, sulfuric acid, carbonic acid, nitric acid, all of those. You can choose to draw those little diagrams or not. It's up to you. A sample type of question that goes along with this concept would just be they'd give you a bunch of formulas and they would all be oxyacids and you'd have to say which one is the stronger acid. So really all you have to do is know the relationship between how many oxygens there are and the strength of the acid, and then you need to know the why part of that question too. So the more oxygens you have, the stronger the acid is going to be. And the reason for that is because the amount of oxygens you have affects the polarity of the molecule. So because oxygen is super electronegative, right? So on this molecule up here, well, I'll start at the bottom. This molecule down here, hydrogen is partially positive. I've got two electronegative things pulling on the electrons. So the dipole moment is going to be over to the right, right? This side, the arrow points to the negative end. All of these molecules are going to have dipole moments that go in the same direction. The difference is that this molecule up here is going to have a bigger dipole moment. This negative is going to be a lot bigger than the negative of this molecule, the negative of this one, because there's more oxygens. There's more electronegative elements pulling on electrons. And so that means that this is held very loosely onto that molecule, and so it's going to fall off very easily. You're going to have greater dissociation of hydrogen, and if you have greater dissociation of hydrogen, you have a stronger acid. So more oxygens make it more polar, easier for the hydrogen to dissociate. All right, the main purpose of this is to show you a type of ion that forms. Shows up maybe as like one multiple choice question usually. Something called a complex ion, okay? And really, you can remember that name because this is an ion because it has a charge. And it looks kind of complex compared to the other ions that we've been dealing with. So these are called complex ions because they form when you have like this highly charged metal and some other molecules that come and they like stick to that ion, but the ion still has the charge. Because if you think about what's going on in this, I've got aluminum, which has a positive 3 charge, and I've got 6 water molecules that come and like attach themselves to it. By the way, this is called a hydrated ion also. Hydrated ion because you have this water that's attaching to it. If aluminum has a positive 3 charge, remember all these water molecules, H2O, they've got a negative end and they have 2 positive ends. Those negative ends of the water molecules attract to the positive charge of the aluminum atom. And so it just so happens that like 6, usually it happens to be like 2 times whatever the charge is. So the charge is plus 3, so usually 2 times that. 6 water molecules come and stick to that and you get this hydrated ion, complex ion. When that dissociates, you end up with aluminum and then one of those water molecules breaks apart. 5 of them stay together and you're left with that 6th water breaks apart into a hydrogen ion and then leaves it with hydroxide right there. So it becomes acidic when it's in a solution. Okay. I have just 2 more basic equations to write. Acid-base properties of oxides. Do you guys need me to go back?
No, I don't.
Sometimes this is also referred to as a coordination complex. So just keyword complex. If you see that, mostly it's an identification type of question on the multiple choice part. All right, next one. We've done this actually before, probably in chapter 4 when we had to write net ionic equations and stuff for acids and bases. But just as a reminder, since we're dealing with it now and talking about strength of acid and base things, if you have a metal oxide plus water, you're going to get a base. So a metal oxide would just be any metal attached to oxygen, K2O, plus water, which is HOH or H2O. You're going to get potassium hydroxide. And then you need to balance that. That's balanced. Okay, so you get potassium hydroxide. Now the thing that you need to pay attention to with this, first of all, you just need to memorize metal oxide plus water gives you base, so you're going to end up with that metal hydroxide as your product. The thing that you have to remember with this is that if you end up with a metal hydroxide that is a strong base, you cannot write your product like this because strong bases dissociate, they break apart. And so you would not get credit for this as an answer. What you would have to write instead would be the dissociated products, because this is a strong base that forms, so I would end up with 2 K plus ions plus 2 hydroxide ions as my product. So you must show the dissociation if it's strong. Okay? Otherwise, it doesn't count. So just pay attention to that. And then this is the last thing. Non-metal, so metal oxides plus waters give me base. a base. A nonmetal oxide plus water gives me an acid. I'm going to give you 2 examples. Nonmetal oxide, let's see, first example, diphosphorus pentoxide plus water. If you just remember that a nonmetal oxide plus water gives you an acid, then you're going to put your product as an acid, and the only one that has phosphorus and oxygen is H3PO4. Okay, phosphoric acid, so then you can balance it. Now, phosphoric acid, is that strong or is that weak? It's weak. If it's weak, you leave it together, okay? If it's strong is where you show the dissociation. So for this example, SO3 plus H2O. Now in this one, this oxygen is going to come over here and make it SO4. So you're going to end up with H2SO4, sulfuric acid, which is strong. So you cannot just write sulfuric acid as your product because it's a strong acid, and so it's going to dissociate. Not only is it a strong acid, but it is a polyprotic acid. Remember we talked about those, which means that it breaks apart in steps. And so you want to show the first step because that's the one that's going to happen first and also the most. And so my product here is actually going to be H plus HSO4 minus. So you show the dissociation of that first hydrogen and then your HSO4 minus. Okay, so if it's strong, you need to show it dissociated. If it's weak, you leave it together as your product. That's it. I guess.